Okay, so going through the questions in the order they appear in the purple book and just talking through what I did. So quickfire questions, number 1. Write down the formula for speed. Speed equals distance divided by time. If it says to write down the formula, you have to use the words, you can't get away with the symbols. Name 3 units you could use to measure speed. Well, the standard one is meters per second, but you could also use miles per hour, or you could use kilometers per hour. Miles per hour can also be written as miles per hour, and kilometers per hour can be kilometers per hour. So there's meters per second is the main one, miles per hour and kilometers per hour in either version are the next kind of 2. There are others. You could have centimeters per day, for example, depending on what you're measuring. Question 1 of the practice questions. A racehorse ran 402 meters in 22.8 seconds. Find the speed. So speed is distance over time. 402 meters divided by 22.8 seconds. Use a calculator, we get so that gives us 17.6315 etc. meters per second. So they've gone to what we call 3 significant figures here, so we'll do the same. So 17.3 meters per second. Okay, carrying on. Question 2. Bernard the snail moved 38 centimeters in 140 seconds. Trick here is centimeters and seconds, but the answer they want centimeters per second, so it's fine. We can leave that as it is, so we don't have to change the units. So same calculation. Speed is distance over time. 38 centimeters divided by 140 seconds. Again, use a calculator. That gives 0.27 centimeters every second, so the answer is 0.27. Always useful to put the units in the calculation, because then you can check it against the units for your answer. 15 minutes to reach the beach and walk 700 meters. What speed was she travelling at in kilometers per hour? So this one's sneaky because they want kilometers and hours, but they've given us meters and minutes. The first thing to do is change the 700 meters into kilometers. So there's 1,000 meters in a kilometer, so divide that by 1,000. So that's 0.7 kilometers. And the next one is to change minutes into hours. So each hour is 60 minutes. So 15 divided by 60. I mean, it's obviously a quarter of an hour, so 0.25. So that one is 0.25 hours. So now we have kilometers and hours. We can get our answer in kilometers per hour. So our answer is going to be speed is distance over time, so we've got 0.7 kilometers divided by 0.25 hours. Again, use a calculator. That equals 2.8 kilometers per hour. So the answer there is 2.8. Chris walked 0.5 kilometers to the beach at 0.1 kilometers per minute. How long did it take him to get to the beach? So we've got kilometers per minute, and that means we're going to get the time in minutes, so that's okay because it matches. So we take our speed, distance, time equation. Speed equals distance over time, and this time it's asking us to work out how long it took, which is the time. So if you look at the time, if you cover that one up, then you're left with distance divided by speed, because the D is on top of the S. So we have time equals distance divided by speed. So the distance is half a kilometer, 0.5. The speed is 0.1 kilometers per minute. Again, use your calculator for that. That equals 5, and it's kilometers over kilometers per minute, which equals just minutes. So the answer is 5. Okay, in this question, the marks are 50 centimeters apart, but we want to work out the speed in meters per second, so you have to convert 50 centimeters into meters. So centimetres, there's 100 of them in a metre, so that is half a metre or 0.5. So that's something that he's doing, that's 0.5 metres. And then we're either, if we're calculating the speed, using speed as distance divided by time, so the 0.5 divided by how long it took, that will give us the speed. Or if we're working out the time, we use time is distance divided by speed, so distance divided by the speed. So top one, we've got 0.5 metres divided by 10 seconds, that gives us 0.05 metres every second. Second one, we've got 0.5 metres divided by 2 seconds equals 0.25 metres per second. Third one, we've got 0.5 metres divided by 5 seconds, that gives us 0.1 metres per second. Now we have to swap it around working out time, so time is distance over speed, so for D we've got 0.5 metres divided by 1 metre every second. That equals 0.5, so that's 0.5 seconds. For E, we've got 0.5 metres divided by 2.5 metres every second, so that takes 0.2 seconds. And for F, we have 0.5 metres divided by 0.4 metres every second. That gives us 1.25 seconds. So part A, what's speed liquid C? Oh, we've just done that calculation, so it's 0.1. Part B, how long did the ball take to pass through the marks in liquid D? It took 0.5 seconds. How long in seconds would the ball take to pass through 15 metres of liquid E? Okay, so 15 metres, so we need to know how long it takes. So remember, time is distance over speed. So if it's going through 15 metres divided by speed, which is 2.5 metres every second, that equals 6 seconds. And then how far in metres would through liquid F would the ball travel in 23 seconds? So how far is distance? So again, using our triangle, distance is speed multiplied by time. So the speed is 0.4 metres every second. Multiply that by the 23 seconds that it's falling for. That gives us 9.2 metres. That's how far it would fall in that amount of time. Okay, on to the next set. So this says, what does acceleration look like on a distance time graph? Slightly badly phrased question. The acceleration is the rate of change of speed. So if you have a straight line on a distance time graph, nothing's changing. So here it's not moving, so it's got a nice steady speed, a straight line, but here it's travelling at a steady speed, so it's moving the same distance every second. So acceleration means the steepness of the line must be changing, so it must be where it curves. So the answer for part 1 is just acceleration looks like a curve, not a straight line. So the car and a van are driving towards each other. How would you calculate the speed of the van relative to the car? So when two vehicles are moving towards each other, their relative speed is added together, because as far as one car is concerned, the other car is moving towards it because of it moving and also because of the other vehicle. So for question 2, you would add their speeds together. Because they're moving towards each other, you add the speeds together. Cyclist and a walker are travelling in the same direction. How would you calculate the speed of one relative to the other? So when things are moving in the same direction, if they're going with the same speed in the same direction, their relative speed would be 0, so basically you're taking one from the other. So the best way to phrase that is subtract slower speed from the faster speed. You could just say subtract them, that would probably be fine as well. So we've got here the distance of a robot vacuum cleaner from its charger against time. Describe the motion between 0 and 1 minutes. So it's only asking between 0 and 1 minute. So here's time, it's in minutes, so 0 and 1. So what we've got there is it starts off, it's not moving at all, and then it's curving up and getting steeper, so that means it's getting faster. So I would just say, accelerating. Accelerating, or you could just say getting faster. And we know that because it's an upward curve. Then it's asking us to calculate the speed of the cleaner between 9 and 10 minutes. So calculate speed, meters per second. Check the units. We've got meters. Here we have minutes, so we'll need to watch out for that because here we want seconds, so we're going to have to convert. So let's find the 9 and 10 minutes. There's 9, there's 10. So at 9 minutes, it's got a speed of, it's 4 meters away, sorry. At 10 minutes, it is 1 meter away. So it's moved 3 meters and it's taken it 1 minute, which is of course 60 seconds to do so. So to calculate the speed is distance over time. So it's moved 3 meters and it's taken it 1 minute or 60 seconds to do so. So 3 divided by 60 is 0.05 meters every second. Okay. The question will carry on. So in what direction is the vacuum cleaner moving between 9 and 10 minutes? So again, if we look at the 9 and 10, the line is going down, so it's getting closer or back towards the charger. So it's heading back the way it came or back towards the charger. So in terms of the direction, best way to put it is back towards the charger, which is in effect the starting point. That's where it began. So called 2 periods on the graph where the vacuum cleaner is not moving. So not moving will be the distance doesn't change. So let's just have a quick look here. We want 2 flat areas. Well, there's 3 we could choose from. Look, it's not moving here, it's not moving there, and it's not moving just there. So there's actually 3 places we could choose for that one. Part E, draw an arrow pointing to the part of the graph where the vacuum cleaner is moving fastest. So the fastest movement means it's covering the greatest distance in the shortest amount of time. So we're looking for the steepest part of the graph, the steepest line. So we could work out the slopes, but actually if you just look at this, that's a fairly shallow slope. That's fairly shallow going the opposite way. That's quite steep. That one there looks like the steepest. So that is the point where, let's label that, that's part E. They were part D, weren't they? So this is the point here where it's steepest, so that's it moving the fastest. Remember, the gradient or steepness of the slope tells you the speed. Question 2. The diagram below shows 2 trains are moving towards each other on separate tracks. What is the speed of train B relative to train A? Well, they're moving towards each other, so you simply add them together. So we've got 30 plus 40 equals 70. They're both miles per hour, so the answer is 70 miles per hour. A car is overtaking a school bus on a motorway. Calculate the speed of the car relative to the bus. They're moving in the same direction, so you take one away from the other. So we've got 73 minus 56 equals 17. So the car relative to the bus is travelling at 17 miles an hour. Okay, challenge yourself. The car and the bus both put into a service station 25 miles after the car overtook the bus. How many minutes sooner does the car arrive than the bus? So the car has to travel 25 miles and it's travelling at 73 miles per hour. So the car is going to take 0.343 hours to get there. The bus has to travel the same 25 miles, but it's travelling at 56 miles per hour. So it's going to take 0.446 hours to get there. So the difference between these two times, do the larger sum or larger time take away from smaller time, so 0.446 minus 0.343. So the difference between them is 0.103 hours. But they want the answer in minutes, so each hour has 60 minutes, so multiply that by 60. Gives us an answer of 6.21 minutes. With rounding, anywhere near 6.2 minutes would be absolutely fine. Okay, on to the forces questions. So, what are forces? Forces are basically pushes or pulls. Pretty much all forces can be. They are measured in newtons, capital N. 5 things that forces can make objects do. So the key thing is, it's forces all about change. So you can make an object change its speed, which can in other words be get faster or get slower. They can make an object change direction, so change the way it's travelling. They can make an object turn, if it's like a lever or a seesaw, or they can make an object change shape. There's a difference between balanced and unbalanced forces. So if they're balanced, then the resultant force is 0 and nothing changes. Whereas if they're unbalanced, the resultant force is not 0 and something will change. On to the practice questions. Each picture shows a situation where forces acting on the object. Next to each one, write down the main overall effect of the forces on movement, choosing the following options. So a cyclist starts pedalling, so if they start pedalling, they're going to speed up. Parachute on a drag racing car opens, well, assuming it was already moving in the first place, that means that's going to slow down. Trickster hits a ball that has been bowled to him. I mean, it's going to actually temporarily slow down, then rapidly speed up, but I think the key thing here is it's making it change direction. That's the main effect. The ball will probably squash slightly during the process of the collision, so actually it also changes shape a little bit whilst it's happening, but it does say what is the main overall effect. Okay, moving on. Tessa adds a layer of whipped cream and a strawberry on top. 2 forces acting on the strawberry, upward force on the cream, a downward force of the strawberry's weight. What will happen if the 2 forces are balanced? If they're balanced, nothing changes. So basically nothing will happen. If the strawberry's weight is larger than the force on the cream, then the strawberry is going to accelerate in that direction, so it's going to sink into the cream. As it sinks further into the cream's going to push back more until eventually it stops the strawberry and it sits still, hopefully. So forces acting pairs that oppose each other. So you're sat on the chair, but your weight is pushing down on the chair pushes back up against you. That's an action force and a reaction force. Forces can't be seen, but the effects of a force can be seen. Objects don't always need to touch to interact. The something pull between planets, that's going to be the gravitational pull. Between planets, forces between something and forces due to something electricity, so that's going to be the forces between magnets then. These are all non-contact forces, and the forces due to static electricity or electrical charge. are all non-contact forces. For the events below, write down whether the forces are balanced or unbalanced. So this is basically whether something is changing or not. So if the vase is standing on the shelf and nothing's changing, then the forces must be balanced. A cyclist starting off is getting faster, so they must be unbalanced in order to help the cyclist speed up. A car slowing down is obviously changing, so also unbalanced. Ski jumper accelerating down the slope, so they're getting faster, so something is changing, so it again must be unbalanced. A marathon runner going to steady speed, so if it's a steady speed it's not changing, so it must be balanced as long as it's a straight road and they're not changing direction. So on to page 46. Friction always opposes motion, so it always acts in the opposite direction to movement, or the attempted movement. Why do objects moving through air or water feel air resistance? That's because they are basically hitting or being hit by the air or water particles or molecules. That means that they're both contact forces, of course. Why is the sheep jumping out of a plane slowed down when it opens its parachute? Well, it only does that if it's already reached a really high speed, but the reason will be the parachute gives it more drag, which is another word for air resistance, so it increases drag, which slows the sheep down. So the sheep still falls, but the parachute will help slow that fall. But it's only if the sheep is already going faster than the parachute would allow. Describe 2 ways in which friction is an advantage when riding a motorbike. Ooh, only 2. So first things first, you need friction between the tyres and the road. First of all, to help you speed up. Otherwise, if the wheels just span, they wouldn't be able to push against the road to actually make you go anywhere. Also, to help you slow down. And also, to help you turn or change direction. So actually, we've got the 3 reasons in there. Another reason why it might be an advantage, helps you stay in the seat, I suppose. If you had no friction, you'd slide off the seats. You could put that as well. Describe 2 ways in which friction is a disadvantage when riding a motorbike. So you've got friction in all the moving parts creates heat. So creates heat, which is basically stealing energy, so it's waste energy. Where there are moving parts, so the engine, for example, gets really hot. Another way it's a disadvantage when riding a motorbike, well, it can also slow you down when you're trying to speed up, so it can act against or work against you trying to accelerate, so against the movement. Anything along those lines would be absolutely fine. State the technical term for a shape designed to minimize friction, so we call that aerodynamic. Or sometimes it's called streamlined. Either of those terms is absolutely fine. This kind of a form has opposing forces acting on due to gravity and air resistance. What is air resistance? We've kind of already answered that, but it's the force due to contact with air particles or molecules, doesn't really matter which. So when he first steps out of the plane, so first of all, when he first steps out of the plane, he's going to accelerate downward. And the reason he does that is because he has his weight is acting down. I'll just add that onto the diagram. There's his weight. And because he's not moving yet, he hasn't really got any air resistance acting up. And so we could add a little or no, I was going to put drag instead of air resistance because it's shorter, acting up. So in other words, the key thing there is what he has is a resultant force down. So if the resultant force is down, the forces aren't balanced, he's going to get faster. He starts to fall more and more quickly. Describe how to the air resistance. Well, as he's falling faster, he's hitting more air every second. So the air resistance, just as described, you don't have to explain why. So the air resistance is going to increase as he gets faster and faster. Because he's hitting more air every second. What happens to the air resistance when the skydiver parachute opens? It suddenly increases a lot more, because when the parachute opens, suddenly you've got a lot more air resistance than you had before. So on here, you've still got the same weight down as you had before. When he first opens the parachute, suddenly we've got a lot of extra air resistance acting up, acting against the fact that he's trying to fall down. So then he's going to slow down, because at the moment he's got a greater upward force and he has a downward force, so he's going to start slowing down. As he slows down though, the air resistance gets smaller until eventually we reach the point where the air resistance and the weight are then equal and opposite to each other. And when that happens, all the forces are balanced again, which means nothing changes, so he'll keep falling at the same speed. So once the parachute is opened, initially he'll slow down a bit, but once it's all evened out, we can just put the forces of weight, which is down, and air resistance, which is acting up, are balanced. Once they're balanced, there's no resultant force, so once there's no resultant force, that means nothing changes. Once he's landed on the ground, of course, when he hits the ground pushes up with a really big force, which slows him down almost straight away. So he stops moving once he's landed on the ground. The ground pushes up against the movement, of course, which is down into the ground, because he was falling down at the time. Okay. So, quickfire questions. If the forces acting on a stationary object means it's not moving or unbalanced, what will happen to the object? Well, it's going to move or accelerate, isn't it, in the direction of the force. If the forces acting on a moving object are balanced, what will happen to the object? If it's already moving, it will stay at the same speed. It will also keep moving in the same direction. In other words, because the forces are balanced, nothing's changed. When should you subtract the force arrows in a diagram? Well, you subtract them if they're acting in opposite directions. So if they're working against each other, you subtract one from the other. And the opposite is true if you add them. If they're helping each other, so if they are in the same direction, then you add them. So it's all about which way the forces are trying to push or pull. The diagram below shows a mass hanging from an elastic bungee cord after it's been dropped. The force of gravity acts downward on the mass, and the force, don't like that, the force of gravity should be the force because of gravity, i.e. weight, but we'll go with it. Which diagram shows the mass when it is speeding up on the way down? So speeding up means getting faster, but as it's falling. So we need forces that are unbalanced and in a resultant force or large force acting down. So that's got to be C, because here we have 10 newtons down and only 5 newtons up, so it must be speeding up on the way down. It can't be this one because they're balanced, and it can't be this one because that's acting up, so that's got to be slowing it down. Speeding up on the way up, so this could be on the way back up, larger force on the way up against there, so that's this one here. Steady speed is when the forces are balanced and nothing changes, that's got to be A. Okay, question 2. Diagram on shows a mug resting on a table. The force from the table, so that's the support or reaction force on the table, is 0.5. What is the weight of the mug? Well, if it's resting on the table and nothing's changing, they must be balanced, so we must have the weight of the mug must also be 0.5 newtons. Car is travelling on the road at a steady speed. So steady speed means nothing's changing, which means the forces must be balanced. So an arrow on the driving force must be forward, and it must also be 400 newtons. Surface of the road it's travelling on changes, and the friction in the road drops by 75. So if this drops by 75, then this will become, the 400 will drop down to 325, which means if we still have the same 400 forward, combine those, that means we're left, instead of it being balanced like it was before, we now have a resultant force of 75 newtons acting forward, which means if that's the resultant force forward, it's going to accelerate. So the question is describe and explain to them what happened to the motion of the car. So it will speed up because there is now a resultant force acting forwards. You could possibly get away with saying it's unbalanced. Okay, for the challenge, we have a modern replica of a ship. During the voyage, the wind turns suddenly, the ship finds up heading into the wind and the current. The line below shows the ship using its engine to travel forwards. Calculate the overall force. So what we've got here, we've got two forces acting against the motion, so let's add those together because they're both helping each other. So we've got 4,000 newtons from the wind and air, and 6,350 newtons from the current and the water resistance. So in total we've got 10,350 newtons acting against the motion, and then of course we've got a forward force of 10,100, so we need to take those away from each other to calculate the overall force. So do the 10,350 minus the 10,100 that's acting forwards. That leaves us a total resultant force of 250 newtons to the right, or backwards in this case, 250 newtons. The question says, what effect will this have on the motion of the ship? So reading the information, it was travelling and then it suddenly finds itself heading into the wind. So it was moving with the engine forwards and then suddenly it's now facing into the wind and the tide. So that means it's going to slow it down. So this will slow the ship down, and the reason is because the resultant force is backwards against the motion. Okay, on to the pressure questions. So, when a formula used to calculate pressure, again if it's the thing you have to put the words in, so pressure equals force divided by area. So normally that would be in newtons over square meters, because force is in newtons and area is in square meters, but sometimes you can have newtons in centimeters squared, or square centimeters instead. Is atmospheric pressure higher at sea level or atop a mountain? Why? So it's higher at sea level. Quite simply because there's more air above you pushing down. That's why you have pressure. So we just put here, there's more air above you pushing down. So more air molecules or particles above you pushing down on top of you. Okay, so it's stationary watercraft, personal watercraft floating in the water. So watercraft has a weight of 300 newtons, sorry, 3,000 newtons straight down. So if it's stationary and nothing's changing, then there must be an equal and opposite reaction force called the upthrust, which must also be 3,000 newtons. Draw and label 2 arrows on a diagram. Oh, done that. Explain what stops the watercraft sinking despite its weight. So this is to do with the fact that there is water pressure pushing on the object where the water is all around and pushing in all directions. So there's obviously more water underneath and pushing up, which creates the upthrust, and that causes it to float. So to phrase that, explain what sorts of watercraft sinking despite its weight, we can just put the water pressure creates up thrust to counteract the weight. We could possibly add here that the deeper you get, the more water pressure there is, which is why there's more up thrust on the bottom of the boat pushing up than sort of pushing on the sides. But actually the question doesn't really ask for that, so we don't need to go into that level of detail. And then on to the last page. So hammering a nail into a wall with a force of 12 newtons. Got a small area here. What pressure exerted? Okay, so pressure equals force over area. So we've got a 12 Newton force divided by 0.1234 noughts after the decimal point, square meters. So use a calculator for this. 1,2,3,4 noughts after the dot decimal point. So that gives us an answer of 1, 2, 3, 4, 5 noughts up in here. I'm going to put some commas in to make it easier to work out what's going on. So 1,200,000 newtons per square meter. So 1,200,000 newtons per square meter. Count your noughts very carefully on questions like that. In pascals, well, it's the same because newtons per square meter are the same as pascals. So it is also exactly the same pascals. That's because newtons per square meter are exactly the same as pascals. They are the same thing. Schmidt's nail hits the wall with a hammer. Explain why the hammer can't penetrate the wall even though the nail can. So this is basically to do, if you think about the end of the hammer, it's a much larger area. Oh, that's a beautiful hammer drawing there. So that area is much more than the pointy bit of the nail. So that's the reason why. So we put here much larger area, and if you put a larger area into the pressure equals force over area equation, if the force is the same but on a bigger area, you get less pressure. So we can just put here much larger area, so less pressure. Max stands with both feet on the floor. He exerts pressure of 12,000 pascals on the floor. State what pressure he'll exert on the floor if he lifts 1 foot off the floor. Explain your answer. So assuming his feet are the same size, what he's done there, he's got the same force as before, but now he's got only half the area. So if you think pressure equals force over area, so if he suddenly made his area half of what it was before, so that is twice as small as it was by lifting 1 foot off the ground, but he's got the same force, that means his pressure is going to get twice as big. So what will happen, so what pressure he'll exert, so it's going to be twice as much, so it's going to be 12,000 times 2, which of course is 24,000 pascals, and we explain why, because he has the same force, which is actually his weight, acting on half the area. That stands with both feet on the floor. The area of contact between the soles of his feet and the floor is 0.06. What does he weigh? So this is with both feet, the area of contact soles. That's this whole thing. Okay, so this is so if we take our pressure equals force over area equation, and we're trying to now work out the force, which is his weight. Force is in the top, so pressure and area next to each other. So therefore, force equals pressure multiplied by area. The pressure before was 12,000 pascals multiplied by his 0.06 square meters. 72,000 newtons. That would make him incredibly heavy. I'm just going to check I've done that calculation correctly. So 12,000 times 0.06 is 720. Watch out for that when you're doing your calculator buttons. very easy to get the wrong number. That's about 72 kilograms. That makes much more sense. Okay, let's go on to the challenge. Some crisp packets are packed in a special mixture of gases to ensure they remain fresh and crispy. Explain why a packet of crisp post at sea level expands when taken up a very high mountain. So very high, the atmospheric pressure is less. So when the crisps are sealed in their packet, there is some air sealed inside with them, and this is at the pressure you get when it's lower down. So then if you take them really high up a mountain, the surrounding pressure, because you're higher up, is now less, which means because we've now got more pressure inside and less pressure outside, that creates an overall pushing outward force, which is why the crisp packet expands.